Okay, so this is for the Noonday project, and we're putting together two videos. One to show you how to collect data outside and measure the angle of the sun. And this tutorial is to show you how to go through the calculations for figuring out the circumference of the Earth. Okay, so this is a picture of the Earth, and our goal is to figure out how far it is to go all the way around one circumference. Okay, and this is replicating a method that Eratosthenes had pioneered 2,000 years ago. All right, now the first thing I'm going to do is give you a circle, because this circle is a model for the Earth. Okay, and sometimes we have to keep in mind some of the boundaries and limitations to our model. Okay, but we're going to use this to represent a cross section of the Earth. Okay. Now, if I give you an example here, I'm going to give you a piece of this cross section. Would you be able to figure out how big the entire circumference of this circle originally was? Okay. Now, I'll tell you that there are two different methods. One is to just simply use the radius, so 2 pi r would give you the circumference. And here we come up against the boundary of this being a model of the Earth. We can't dig all the way through to the Earth to figure out this radius. Okay, so we'll try to make use of this distance along the outside of the circle. Could you figure out the entire circumference given this measurement? Okay, and if you think about that for a few minutes and see what you can come up with, I think that this is a simple replica of what you will do on the bigger scale. Okay, but what you would do is you would take this measurement here probably and multiply it by 4, figuring that this is about 1/4 of the way all the way around. Now what you would do is set up an equation such as this, where the ratio of the distance from A to B over 90 degrees is equal to the ratio of the distance all the way around the circumference over 360 degrees. So if this is 20 centimeters, it would have been 80 centimeters all the way around the original circle. Okay, very simple, very straightforward, but it gives you a sense of what we're going to try to do to calculate the Earth's entire circumference. Now, if I give you a little more difficult example, okay, this is the same thing, except now we don't have 90 degrees, which is very handy and very easy to work with. Okay, how would we again figure out the entire circumference given this piece of pie to work with? And it's a little bit harder because we now have a degree measure that's not 90 degrees. Okay, but we can set up the exact same proportion, right? We can figure out the angular measurement, and I can put the protractor on here, and it looks like about 37 degrees. Okay, and then I can measure this distance here, and again set up the exact same proportion. And that's modeling what we're going to do in the Noonday project. However, again, we're up against another boundary. We have difficulty measuring this interior angle. All right, so what Eratosthenes recognized was that if he could measure the angle up here on the Earth, this representing the Earth's surface, if he could measure the angle of the sun here, that angle is the same as the interior angle. Okay, so this angle A is the same as angle B, and you don't have to dig into the interior Earth to measure it. And then the only other bit of information you need to set up that proportion is the distance along the Earth's surface. Okay, so that's the math that he was using. Now what gets a little bit one step even more complicated for the Noonday project is this measurement, this location here, we're assuming is at the equator. And that's not always going to be the case for what you are doing. This looks more like what you will be dealing with. You're at location A or B, okay, and then you're going to collaborate with another school from A or B, the other one, and C is at the equator, but we don't necessarily have someone to collaborate with at the equator. Okay, so in this case, what we do is, instead of just taking the measurement that you would collect, what we want to do is collect. You want to take that measurement, okay, and if you recognize that this angle here is the same as this angle here, okay, you recognize that we don't quite have the interior angle AOB. We don't have that angle. We have AOC, and that's not quite it. But if we can subtract from this angle here, if we can subtract this angle, which we can get from location B, if we subtract that angle from AOC, then we actually get this interior angle. Okay, so this is the interior angle that we want, and this is the distance that we want. And then once we have that, and that's what you're collaborating with other schools to do, we can set up a proportion, the latitudinal distance between A and B. Okay, divided by the difference in sun angle between A and B. Whoops. So there'll be the difference between what was measured here and the angle that's measured here is going to equal to x over 360. Solve for x, and you have the circumference of the Earth. Now, there's two little assumptions that are embedded in here, and it's good to revisit with students. The two assumptions are that the Earth's surface is curved. Okay, Eratosthenes recognized that and was further exploring to figure out how big it was. Okay, so students don't necessarily readily accept this or understand how we would know this. Okay, but by figuring out that at the exact same time two locations have different angles for the sun, that would suggest then that the Earth's surface is curved. The other assumption is that the rays from the sun are coming in parallel, and that's because the sun is so large and far away. So when we go back to this drawing, all my lines were drawn exactly parallel because the sun is so large and so far away. But again, it is an underlying assumption to the calculations we're doing. Okay, so the other tutorial that we'll have for you is measuring the sun's angle outside, and then you can use that data to collaborate with another school and try to calculate what the circumference of the Earth is.